Here are the leaders I've invited. These are the students from the morning class. And the afternoon class is in this list in no particular order. Those of you that are from the afternoon class, do you have your printouts? Raise your hand if you have your printout ready and signed and stuff. Okay, a couple, three. Hand them to me at the end of class. That'll be great. Okay. And the rest of you, what we want to do is, I want to get a reply from you if you say yes or no ASAP. And it's all right to say no. You don't have to be an SSG leader. You're doing me a favor. I reward you by allowing you to skip the final if you do the favor. So try to get that stuff. Now, I'll be in my office all day tomorrow till about 5 o'clock. So get that to me if you haven't got it today, get it to me by 3 p.m. tomorrow. And then at 5 o'clock tomorrow, we're going to have special study group sign-ups. So for the rest of you that are not on this list, you'll be able to sign up to study 6 people at a time with one of these guys, okay, if it meets your schedule. The place to start is by looking at your grades page where it says your group for SSG. So what you have to do is ask yourself, are you in group 1 or group 2? And so here's what it's the very first line of the grades page. It says your group 2 may sign up only after 7 p.m. So you're going to either have a 1 or a 2 there. Special study group leaders, you guys have zeros, okay, because you're already in a special study group. Okay, so if you're in group 2 like this guy, okay, you may not sign up until after 7 p.m. Group 1 is going to have first shot, and to figure out if you have first shot at 5 p.m., just look at your grades page, very top line here. And this way, the students that need extra study the most have the first shot. And there should be enough for everybody in group 1. And there will be spots left over if all the special study group leaders agree to lead a group. So that's a possibility. Now, this is the first thing you do. You look and see what group you're in. And then once you've... Make sure you figure out what you're doing here. All right, you don't want to mess out. Group 1 starts signing up at 5 p.m. and then Group 2 only after 7 p.m. So Group 1 gets a 2-hour window. You pick and choose. You should be able to find, hopefully you'll be able to find something that fits your schedule between Saturday morning and late Monday night. Now what you do is you follow the SSG icon. So go to the Web Courses homepage and look for this icon. It looks a little bit like this on the homepage. Here it is, down here by the picture of Galileo. And right now that is linked to nothing, but it will be linked to the entry page for sign-ups at 5 o'clock tomorrow. Okay, so you'll click on that, and then you'll come to a page with the Simpsons riding an invisible bicycle. It looks like this. And you may think to yourself, Dr. B, why are you having a picture of the Simpsons riding in a bicycle? What does that have to do with physics, riding an invisible bicycle? Well, it's a memorable photograph, a memorable image, and you won't forget it. And when you see it, you'll know, yep, I'm in the right place. And then down here towards the bottom, this is the actual thing that you click. That's what you click to get into the actual sign-ups. So, by the way, this Simpsons page, let me get to it again. Okay, I'm also going to put the actual schedule. So you won't be able to click through until 5 p.m. But you'll be able to look at the schedule as it comes in. Now, as it just so happens, I have 3 special study group leader printouts right here. So I know 3 of the group schedules, and by 5 p.m. tomorrow, hopefully we'll have all of them in place. So you'll be able to look at the schedule and think, well, I can go to group 7, and you better look up 1 or 2 backups. So you might look at the rest of the list and think, okay, 12 and 13 are going to be my backups. And then you click through, and then you click on the actual group to join it. And my last admonition to you is this. Do not click on a group unless you're absolutely, positively sure that you can make it. Because A, if you can't make it, you're going to do double damages. You're not going to get points. And somebody that could have had those points and wanted to, but couldn't because you clicked, is not going to get any points either. All right? So that's 8 points worth of bonus points in the garbage can. All right? So don't do that. So make absolutely, or as they say on TV, absolutely, positively sure that you can attend. If you can't, you can't. All right? And by the way, do not try to sweet talk the SSG leaders into letting you come into their group. They're restricted to 6. They may not have more than 6 people in that room. And I do not want you to take advantage of them. They may be your best friend, but they're doing me the favor. And I don't want them overburdened with you trying to sweet talk your way into their session. Even if they're amenable to it, I don't want you to do that. All right? Now, let's get back to our physics discussion. Coulomb interaction and the behaviors of molecules. And you might be thinking, Dr. B, what does this electromagnetic stuff have to do with molecules? Only everything. It's all about the electromagnetic interaction. For instance, water. Water molecule, we say that it has a polarized structure. And that means that there's kind of a symmetry line down the middle here. And the red end of the hydrogens are the positive end of the molecule, because that's where the hydrogen protons are. And then the other end, the oxygen end, tends to be the negative end of the molecule. All right, that's the polar structure. It has a pretty precisely known angle. It's called the dihedral angle. The angle formed between the hydrogen atom, the oxygen atom, and then back out to the other hydrogen atom, H2O. And that works out to be 104.4776 degrees. And they've measured that experimentally. It's not easy, but they can do it. Our quantum theory also predicts an angle of about that size. So our theory is in agreement with what they've actually been able to measure. It's a tough measurement, but they've been doing it for a while. They have a fairly good handle on it. Another thing that is true about oxygen and hydrogen in the water molecule is the distance for hydrogen to oxygen is about 0.0958 nanometers. Whoa. That's a small fraction, not even a tenth of a nanometer. And a nanometer is a billionth. So here it is in scientific notation. Sarah, 9.58 times 10 to the minus 11 meters. That's a really small distance. But we have a fairly good lock on that for water. And the same with all the other molecules. The point being that when you're trying to figure out what electrons are doing, the Coulomb interaction between positives in the nucleus, positives in the form of protons, and negatives in the form of electrons, that controls all this structure. You know, how big it is, the angle, even the polarity is controlled by that, by the Coulomb interaction. So if we want to know molecules, if we want to know what electrons are doing in general, yeah, we have to know all about the Coulomb interaction. And so what we're going to be working on today, the brain burner, I like to call it, is going to be a fairly simple, idealized view of a molecule. And we're going to work through that step by step. Now, last time we talked about Coulomb interaction. This inverse R squared force here, R squared in the denominator, means that as distance gets bigger, you know, like by a factor of 2, then the actual force gets smaller by a factor of 1 over 2 to the second power, 1/4. If the distance is 3 times, the force goes down by a 1/9, 1 over 3 to the second power. So it has a real significant effect. Another thing that we didn't go over last time, but which we will go over today, is how this force law accommodates repulsion. Gravity does not have a repulsive effect. It's always attractive. There's no such thing as positive or negative gravitational mass, but there is such thing as positive and negative electric charge. And that is how, in this force law, the switch between repulsion and attraction can occur. Now, if you have a proton, it has the same size positive charge as the electron has negative. Okay? And so the charge on the proton is a plus E. Little e is the symbol for the charge on or the fundamental charge, they call it. So plus E is the charge on the electron, minus E is the charge on the electron. Wait a minute, did I say that wrong? Plus E is the charge on the proton, minus E is the charge on the electron. Okay, that's right. All right. So let's do an example with a proton and an electron and this Coulomb force law, 1 over R squared force. And with this example and this force law, and actually another example after this, we'll show how this formula, Gabby, leads to repulsion. Okay? And let's say that this electron and proton, they're at such and such a distance, and at that distance, the mutual interaction force is 10 newtons. Okay, you can do that. You know, you squeeze them down to a certain distance, and at that distance, the attractive force between them is 10 newtons, plus or minus 10 newtons. All right, now, the attractive force on the electron is going to be leftward. So if we use pluses and minuses for rightward and leftward, then this is going to be a negative force of 10 newtons, negative 10 newtons. And here's my abbreviation. Instead of putting plus 1e and minus 1e here, I'm just putting plus 1 and minus 1. Well, plus 1 in regular parentheses, minus 1 in regular parentheses to denote the electron, plus 1 in the square brackets to denote the proton. All right, so I'm just simplifying my notation a little bit. All right, and you know, k is a positive number, r squared is a positive number, negative 1 is negative, positive 1 is positive. So this quotient here is a negative number, and I said that we'll squeeze r down so that this becomes not just a negative number, but negative 10 newtons. Okay, so that's what this force would look like, and here's the arrow that you could write for this electron. All right, so make a sketch of that proton on the right, the electron on the proton on the left, the electron on the right, and give the electron a little leftward arrow of a certain size. Now, I want you to draw another picture of two protons. I'm going to park mine up here in the same spot. So I'm going to move my electron out and put in a proton. There it is. All right. Now, that one we have the same formula, but it's got different charges in the numerator. Here's the different charges. Instead of a negative one here in regular parentheses, I've got a positive one to represent the fact that I've changed this into a proton up here. So this is your second example, proton to proton. And the force of the proton on that, excuse me, that's in the podcast. That's on the transcript. Nice. Dr. B yawning. Anyways, so you have positive, positive, and all right, that comes out the way it should. It's the opposite. Get my cursor here. It's a positive 10. Positive times, everything's positive, so my net quotient is positive. So what that does is it takes this arrow and it turns it the other way. All right? So and that proton over there is going to be repelled off to the right. And this one here, my initial proton, it's going to be repelled off to the left. But if I'm really concentrating on this particle, yeah, that's going to be to the right. And so that is how this formula accommodates a switch in the force from left to right, from attractive to repulsive. It comes in here in the SIGN of the charges. And when you switch the signs, you switch the direction of the force from leftward to rightward. All right, so this is the electron-proton attraction up here. And down here, that's the proton-proton repulsion. And just as a side note, that conversion constant K, that's Coulomb's constant, it's like a conversion factor to get newtons, because measuring charge dividing by the square of a distance, that's not going to give you kilogram meters per second squared, so you need a conversion constant to do that. Kind of like capital G in the universal gravitation formula. All right. Now, we're going to be working with this formula all day today. All right. So I want to trot you through some of the things that we talked about last time. One of which was this one. This question was the one question we asked last time. What direction is the net electric force on the rightmost proton? And we figured out, okay, this one over here, this rightmost proton, gets some repulsion from the middle electron. So go ahead and sketch in an arrow to the right. Make it a fairly big one. But it also gets some leftward attraction force, so it gets a little bit of pull, Olivia, off here to the left. Now that's going to be a smaller arrow, and if you care about dimensions, it's going to be a fourth of the size of the big arrow, because the distance to the electron is twice the distance to this middle proton. So the distance ratio is 2 to 1. The square of that is 4 to 1. The flip-flop is 1/4, and that's the shrink-down factor for this attractive force here. All right. So here's a sentence that says that the leftward attraction is 1/4 of the rightward repulsion in size. All right. But it also has its own direction to the left. And for that reason, you're going to have a net electric force to the right. Now, in this linear charge array, evenly spaced, you can figure out exactly the proportion of the different arrows in this diagram. Okay, the net force is basically going to be 3/4 of whatever this rightward repulsion force is. So the nearest neighbor interaction, here's the nearest neighbor. Okay, this red proton in the middle. That's the nearest neighbor. It's going to have such and such a size of repulsion force. 1/4 of that is going to be the size of the attraction force, and then the sum is going to be 3/4 rightward, 3/4 of whatever the nearest neighbor interaction was. Now we're going to be working on problems together that allow us to figure out an even tougher net force for a bigger linear charge array. Now, get your clickers out and let's do the first clicker question. And let's see how well you were listening to what we just said. And let me start this question. We're on frequency BB. Bravo, bravo. So if the, oh, hey, you guys, how large is the electron-proton interaction to the rightmost electron? So I'm at this question, it's not written up there on the screen, but it should be the interaction between the electron and the far proton. How big is that interaction? Fifteen seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Pretty good. 10 micronewtons. A few of you chose A and B. If you chose A, no, that's no good. If the nearest neighbor, the interaction between these two is 40, the interaction between this electron and the far proton cannot be the same size. Okay? This is half of it. It can't be half. The ratio is 1/4. Okay? Now, we're going to be aiming for molecules, so we're going to be working with bigger arrays of charges, something like this. But before we do that, let's just trot through a few more concepts to motivate why we are trying to figure out individual net forces. In a regular electrical circuit in your home or in your calculator or your telephone, the electrons are the things that move. It's not the protons. And the reason for that is that the mass of the electron is really small compared to the mass of the proton. The mass of the electron is 1/2000th of the mass of the proton. So if you look at a proton and an electron like this, in terms of charges, yeah, they're the same size, but one's negative and one's positive. But if you look at them in terms of mass, Lindsay, then this is how it would really look. Okay? You'd have a really big proton in terms of mass. The mass is 2,000 times the mass of the electron. So in a regular circuit, for most terrestrial environments, it's the electrons that are moving. So if we focus on electrons and what they're doing, it will be really helpful, even if we're trying to figure out molecules. Now, if you're in an exotic environment like the surface of the sun, then everything forms a current, protons, electrons, and even the nuclei of helium atoms. And a proton is the nucleus of a hydrogen atom, if you think about it. You know, a hydrogen atom is a proton with an electron orbiting around it. If the proton gets stripped off by ionization, then that means all that's left is a proton. And the interesting thing is these currents flow in opposite direction. So, Darion, the positives might be going this way to the left, and the electrons are going to be accelerating to the right. You know, so the accelerations are going to be opposite direction. And so it behooves us to be careful about figuring out what the electrons are doing. And so, as I've said before, figuring out where the electrons go is a big topic, and we're going to try to work out a semi-complicated array like this together and figure out the interaction forces, and then from them figure out a net force, because the net force on a given charge, whether it's positive or negative, will tell you, where it's going to be accelerated and eventually where it is going to go. We want to know that, and so we're going to take this kind of idealized picture of a molecule, an electron, then a proton, then another electron, then two protons, and we're going to try to make sense of the forces acting on this electron on the left. So go ahead and make a sketch of this. And here's the same sketch. And what we're going to do is, first of all, make sure that the 5 charges are equally spaced out. So in your sketch, draw an electron, then a proton, and then another electron, then another proton, and then another proton. And make sure they're, do your best to make sure your sketch is equally spaced, so that each interaction distance between neighbors is the same. Now, if they're not the same distance, it's all right, we can handle that. But for a fairly simple problem, kind of an idealized system, something like a molecule, this will be a good place to start, equal spacing. All right? And what that means is that the distance between these two electrons, the two blue ones, is double the distance between the left electron and the first proton. So here, right in here, this is your baseline distance, your nearest neighbor distance. All right? And then if everything's equally spaced, this guy over here, this second electron, is going to be twice that distance from my object of interest, the leftmost electron. So we'll put a star next to this electron to denote this is the one that we're trying to figure out the net force on. So put a star or a question mark or a check mark or something like that. Okay? So this proton is its nearest neighbor, and that's such and such a distance. This electron is its second neighbor. That's double the distance. And so on, all the way out. This this proton here, the second proton in the array, that's 3 times the distance, 3 times the baseline. And see, the interaction decreases with distance, with the square of the distance. So if you know that the distance ratios are 3:1, for instance, that helps you figure out the size of the forces. This last one over here is 4 distances away. All right? And as I mentioned, this affects the interaction strength. So, for instance, this leftmost interaction here, the leftmost electron gets the smallest pull from this guy. All the protons are going to be pulling rightward on my target. My target's the leftmost electron, and every proton is off to its right, so they're all attracting, and so they're going to give some newtons to the right, however many newtons we haven't decided yet. But whatever they are doing, they're pulling to the right. And this is the smallest one. Now this one is the biggest one. That's the nearest neighbor. Okay, it's a proton. It's pulling right, pulling that leftmost electron to the right. And that's the biggest pull of all the different pulls and pushes. There's some pulls of attraction. There's some pushes of repulsion. But of all the forces, this is the biggest one. And then what we have to do is figure out how to put them together into a net force. So we're going to have to deal with negative signs for leftward, positive signs for rightward, and we got to figure out the sizes. We got a lot of stuff to do here, right? So that's what we're going to do. But our basic strategy is this. If you know the nearest neighbor interaction force, NNF, and if you know the distance ratios, which we do because of equal spacing, we have either 1 to 1, 2 to 1, 3 to 1, 4 to 1, and so on, then you can figure out the net force on any of the particles. The leftmost electron is the one that we're working on, but you can actually use the same techniques to tackle the net force on any of the other particles. Works out pretty nicely. Matter of fact, I might give you one of the interior particles for homework as an ultra brain burner. And just so you have a preview of coming attractions, this weekend, this homework is going to burn the brains in many of you to a crispy crunch, just like Cheetos. But only if you do not participate in discussions. Our discussions area in web courses, I want it to become a beehive of people talking about these brain burners. All right? And if you do that, you'll be able to kind of sort your way through. Darianne is going to be on duty this weekend, and I'll be working in discussions from time to time. And so we'll all just figure it out together. All right? It's going to be really tough. Some of you will have it down pretty much by the end of today. So let's work out a problem and see how you guys do. All right, so here's my main formula. I'm going to either have, in general, E and minus E, or E and E, or minus E and minus E in the numerator. All right, so the only thing that, and that just affects whether it's leftward or rightward. So the only thing that's going to change the size of my interaction forces is the distance, the r squared. That's going to be different for each interaction pair. So here's what we're going to do. For this array, let's say that the nearest neighbor interaction force is 288 newtons. Okay? And if we know that these two babies right in here, my target particle and my first proton, if we know that those are attracting each other with 288 nanonewtons of electrical force, we can figure out all the other forces and then put together a net force. All right? So, the first, and actually, what direction is the nearest neighbor force on this electron? Is that electron getting pulled by this proton or repelled by the proton? Attracted or repelled? Attracted, right? Okay. So therefore this electron is getting pulled to the right, attracted to the right. So the first part of our net force is going to be a positive 288 nanonewtons. Now, let's figure out the nearest, the second neighbor. And the second neighbor is an electron. All right? And it's twice as far as the nearest neighbor. So the second neighbor, I always denote 2NF, second neighbor force. Okay, so the electron on the left is going to get some newtons, some nanonewtons of interaction force from this guy. Now, mental IQ test question. This electron in the middle is going to exert a force on my particle of interest, this leftmost electron. Is it going to repel or attract? It's going to repel. Is it going to repel to the left or repel to the right? Raise your hand if you could tell me the answer to that. Repel to the left or repel to the right? What do you think? Yeah. I'm talking about this one, where my cursor is. Is that going to get a repulsion to the left or to the left? But it's an electron. So doesn't that mean the repulsion is the opposite? Your head just went to the left. So you're staying with that? Yeah. Okay, I couldn't shake her. Good. Yeah, it is to the left. Okay? And its distance is 2 to 1. So the shrink down factor is 1 over 2 squared, or 1/4. Okay? Now, last hour, I got asked that question about 3 or 4 times. Why is it 1/4? And here's the answer. You take the distance ratio and square it. 2 to 1. Square it. 4 to 1. Flip-flop it. 1 to 4. And that's the shrink down factor for the second neighbor. All right, so what's 1/4 of 288? That's 50. Well, 288 divided by 4 is what? Come on, get your calculators out. You're going to need them. What? Yeah, 72. All right, 72. So let's make a diagram here now and put in what we know. Okay, baseline nearest neighbor force is the right word, 288 nanonewtons. All right. Now my repulsion force from the second is 72 newtons to the left, so let's give that a minus 72 nanonewtons. And in the end, we'll add them all up. All right? So now we've got this middle particle, the second neighbor, squared away. But we got 2 more neighbors to go. All right? So, working with nearest neighbor of 288, let's get the pull force from the second proton. The second proton is right out here. Here it is. Right here, this baby. All right? Now that second proton, Caitlin, is 3 times as far away. So, it's 3 times the nearest neighbor distance. So my shrink down factor is going to be what? 1/3, right? Yeah, because the distance ratio is 3 to 1. So flip-flop. So 1/3, right? Well, I see a guy here frowning at me. Now, why are you frowning at me for saying 1/3? Yeah. It should be what?
Reduced by 1/9.
1/9. Why is that?
3 squared.
Right, it's 3 squared. Good. So I couldn't dog you. You guys, I can't break you. You guys are smart. Good. So 1/9 is the shrink down factor. All right. And it's an attraction. The proton's to the right. It's attracting my target particle to the right. So let's see. Now, what's 1/9 of 288? 1/9. It's what, 32? Okay. So 288 times 1/9 is 32. And, okay, let's add another arrow. Here it is. Their arrows are getting pretty small. The biggest arrow is always the nearest neighbor. If you're working with a particle on the end, either the left end or the right end, it's always the nearest neighbor that's got the biggest force. Now, if you're inside, if you're taking one of the interior particles, you have stuff on the left and right. But if you're at the end, the nearest neighbor force dominates, and you can see it in this diagram. All right? So here's the third neighbor. Here's 3NF, the third neighbor attraction force. So we've got this one bagged up, but we still have one neighbor to deal with. So let's get this guy. This one gives us the weakest pull force. All right? And so it's 4 times the baseline distance. And that means the shrink down factor is 1/16, 1/4 squared. And 288 divided by 16 is 20? 18? So how come you went like this? Was this V for victory? Or so the student in the back over here, he went like this. 18. It's like a math professor. I had when I was in grad school, I had this math professor in geometry, advanced geometry class, and he was a really smart guy, but he was up there in the ozone layer, I mean, his whole life. I mean, he just kind of beamed down occasionally to teach class. But he was a good guy. But so he's talking to us one way, and in geometry class, you always prove theorems and stuff, right? So he was facing the class, and he said, "Class, there are 2 ways to prove this theorem." And Dr. B's holding up 3 fingers for the transcript. There. So just like you. So you must be a math. Are you a math major? But you could be. It could be in your future. Anyway. So shrink down factor 288 divided by 16 is 18, as the math department can tell you. Okay, so that's a little teeny tiny vector. And these are the 4 vectors that go into my net force. All right, this is the 4th neighbor force. So this is 4NF, 4th neighbor force. And hey, you guys, you just got to be organized with this. It's every single thing that you do, every individual thing that you do, is not that tricky, but you got to put them all together in the right order, and with a lot of different decisions for each item. All right, so here's so now I've got everything squared away. I've got all 4 interaction pairs. My target particle here, the leftmost electron, that's a member of each interaction pair. And then its neighbors, each neighbor forms the other half of the interaction pair. And we figured out 4 interaction forces. These many interaction forces. Okay? And now we just got to put them together. Here we go. 288 plus 32 plus 18 minus 72. A little bit of repulsion. Total of 266. So you could say, here's my constituent forces up here, and now I've got my net force here, Sarah. Big, nice 266 nanonewtons. To the right. And as I've mentioned, if you're working with a particle on the end, the nearest neighbor is going to dominate everything else. Even if it's all electrons over there, they're not going to overcome. You're always going to have a rightward net force. Now, whatever your nearest neighbor force is, it's going to dominate the direction. All right, now, Colin, question? I can't really hear Colin. Can you speak up a little louder? Yeah. On this, okay, here's these two, 288. This one and this one, it's smaller because they're further apart. The distance is twice what this is. All right, so this one is some distance. This distance here is twice that. So 2 jumps. 1, 2. Okay, so 2 to 1. Square that, 4 to 1, and then flip-flop it, 1 to 4, and that's the shrink-down factor for this force. And that's why this one is 72 nanonewtons, a fourth of 288. And because it's a repulsion force, it's also negative, leftward. All right? All right, and so you just do that for each pair, pair by pair. Another question. All right, let's go ahead and try some questions. Now, what I want you to do is make a sketch. This is the array that we're going to work with. Put a star or a check mark next to the leftmost electron. And what we're going to do is a series of multiple choice questions now, and then a calculation at the end to figure out the net force on this electron. All right? Now, it's a different array. It's arranged differently now. Okay, I've got an electron for my target particle of interest, a proton, and then I've got 2 electrons. And for homework, you're going to have a different arrangement again. I might even give you 6 particles. All right, so, but let's figure out this one. All right, now, the next slide is going to be a question, and it's going to have the same sketch, but it's going to be at the bottom. So let's do the next question. Here's your next clicker question. Force on the leftmost proton, is it an attraction or is it a repulsion? If it's an attraction, is it leftward or rightward? If it's a repulsion, is it... So leftmost proton on the leftmost electron is this nearest neighbor, this nearest neighbor pair right here. Okay? So the force of the leftmost proton on this baby. Go ahead and answer that. Good. And make sure you have this sketched. Make sure they're evenly spaced, because your homework is going to be evenly spaced, and your exam number 3, you're going to see this problem. I'll just tell you right now, there's going to be a problem like this on the exam. I may as well be honest about it. 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Stop. Pretty good. This is it. It's attraction, and a bunch of you I can see voted for B. If you voted for B, you've got the right idea. It is an attraction, but this thing is what we're concentrating on. So if it's an attraction toward the proton, it's got to be rightward. All right. Now let's try another question. Very similar. The force on the center electron, of the center electron on the leftmost electron. Okay, so now your interaction pair column is this one and this one. So second neighbor. What kind of a force does the second neighbor produce on my target? Fifteen seconds. I see people going like this and like this. It's great. Good. That means you're thinking. That's what I want. Five, 4, 3, 2, 1, 0. All right, let's see if we get... Yeah, pretty good. It's repulsion. It's electron to electron, so it's repulsion. And this one here, this guy, my target particle, is getting repelled to the left. All right, so when we get to a force, we're going to have a negative sign with that force to indicate leftward. All right, let's go to the next question. All right. So far, we have some leftward and some rightward. We got a little bit of rightward force. We got a little bit of leftward force, but we haven't figured out the sizes of each. And we have to figure out these two guys over here as well. So these two. All right, so we still got a little bit of work. Let's keep going. Now I'm going to give you the information that you must have, the nearest neighbor force. Here it is. Nearest neighbor force is 576 nanonewtons, so it's a little bit weaker, or excuse me, a little bit stronger. Interaction force between the leftmost electron and the rightmost proton. Okay, rightmost proton is this one all the way out here. Okay, so this is the fourth neighbor force. It's going to be an attraction, but how big is it? And if you don't have your calculator out yet, you better get it out because you're going to need it. Good. I'm glad to see you guys working together. Thirty seconds. I'm really hungry. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Dun, 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 dun. Uh-oh, I see a bunch of you. 20 of you chose B. No, no, no. B is half of the nearest neighbor force. You want a fourth of it. Your distance is 2 to 1. The square of that is 4 to 1. The flip-flop of that is 1 to 4. So your shrink down is 1/4 of 288, whatever that happens to be. Or, oh, sorry, that's not right. What am I talking about here? This is, that's 1/16. All right, so that's 1, 2, 3, 4. So what's 140? What is 144? That's a fourth. It's a fourth of 576. Okay, so that's for this guy in the middle. Ooh. I just gave away part of it. All right, here we go. Now we've just, Dante, you got a question? 36? Okay. 576 here. 1, 2, 3, 4 jumps away. Distance ratio 4 to 1. Square of that, 16 to 1. Inverse of that, 1 to 16. 1/16 times 576 is 36. All right? Now, my wonderful students, now you must burn your brain. Hit the refresh button and put it all together. All right, this is a numeric question. You're going to come out with a whole number. So just work on this carefully. You got to know how to do it on the exam. Definitely coach and kibitz and consult with your neighbors. Matt, how you doing over there? I'll look at it. This is a sight to see. Lovely, lovely, lovely. You guys ready to go? No, I mean, no, not to go home. Ready to type in your question. All right, 30 seconds. Nice try, Zachary. Was that you or was it you? You? Ooh, case of mistaken identity. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Raise your hand if you had 404. Good. Got it. Good. I see a 532 in here. I can't figure out how to get 5. Some of you have 532. I can't figure out how to do that. 404. Now, before I dismiss, I want to give you a couple tips about the exam and special study groups. Question? Yeah, I explained it before we did it. It's just the same procedure that we did. We did almost all the steps already. You're just putting them together. If you want to come to office hours, we'll work it over in office hours afterwards. We're not finished yet, and okay, I guess you guys don't want to have special study groups then, right? All right, your homework for the weekend, number 19, is going to be brain burners all the way. I want you to work really hard and consult with your study partners. Darianne is going to have office hours on Monday at 1 p.m. in the Physical Sciences building. I want you to hit the discussion groups. Hit them hard. Make them a beehive of activity. Just like, you know what? I was watching you guys while you were working, and this place was a beehive of people. I was watching Colin. He was coaching all those people behind him and stuff. It was great, and I saw a bunch of other people doing the same thing. It was great. All right, so do that in discussions. Special study group for bonus points, but you have to be signed up. If you're not signed up and you try to go, you will not get points, and you will get in trouble with me, and I don't want you to ask to squeeze yourself in. All right? If you're not signed up, you're not allowed to go. Group 1, tomorrow, 5 o'clock, be ready to click. Everybody else, 7 o'clock. All right, you're dismissed. Special study group leaders, come on up to the front if you like. Okay, the mic.
China's having her early meeting tomorrow too, right? As well.
For SI?